I've been really looking forward to this last speaker, Yaqub Chaudhary from Cambridge. His talk is entitled The History of the Graphics Processing Unit in Contemporary AI.
So this talk comprises a brief overview of the history of hardware design for consumer 3D graphics, which eventually made way for the same hardware architecture to be used for high-performance computing, which went alongside developments in APIs and programming tools, first for game developers, then for computational scientists. Most of the literature that reveals this history tends to be on the role of GPUs in general purpose computation, and not specifically linked to the role of GPUs in contemporary AI, in making contemporary AI possible, or the role of GPUs is mentioned as a footnote to the revival of AI. Much of the history of GPUs that enabled contemporary AI is drawn from the technical literature on the subject, written for developers and computer scientists, or is to be found in the literature, symposium talks, or promotional communication by the companies themselves, such as the NVIDIA series of textbooks titled GPU Gems. In one of the volumes in this series, from 2011, the editor writes, "The potential is there, and some lucky researchers may find themselves with a Galilean first opportunity to see, study, and model using exquisitely detailed data from projects utilizing GPU technology and these hybrid systems." This was in 2011. This invocation of Galilean first opportunity is quite appropriate. Since 8 years on, we have found that in an increasing number of disciplines, the key challenges are that the problems have become too complex to handle by traditional computer simulations. And we have seen how GPU-based supercomputing and machine vision have offered a digital telescope into unfathomably large arrays of data, opening the vision of scientists to a new universe of complexity and allowing them to see old and new data with fresh eyes. A key aspect of the project that produced the recent image of the black hole is that it was led from MIT's Computer Science and AI department, and image reconstruction was powered by the University of Arizona's El Gato supercomputer, which runs on 140 NVIDIA GPUs. With this new instrument of science, GPU-accelerated deep learning and AI is fundamentally altering methodologies across virtually every scientific discipline. So on the use of GPUs in AlexNet. The current revival of AI research is based on the connectionist paradigm, or artificial neural networks, and extends back to the AlexNet demonstration from 2012, which made a huge step forward in performance in the ImageNet image reconstruction competition compared to manually coded solutions, and is therefore widely considered the breakthrough moment for contemporary AI research. AlexNet demonstrate the capabilities of deep convolutional neural networks in machine vision tasks, and what is often missed from the discussion is that this was achieved by a very efficient implementation of the convolution operation on a system utilizing dual graphics processing units. So as you can see, convolution is being performed stepwise, but in reality, this can be fully parallelized and done in one step across numerous processing units. So the talk will progress through the development of GPUs, focused around one company in particular, because there simply won't be time to discuss all of the other competitors, namely NVIDIA, and the various architectural changes they made to their graphics processing units that set the ground for AlexNet researchers to implement deep neural networks efficiently. So GPUs first became available 20 years ago from NVIDIA, who coined the term, in October 1999 to accelerate rendering performance in 3D video games by handling transform and lighting operations in hardware. The transform stage involves manipulating the vertices of the polygons that will eventually be displayed on screen. And the transformation stage requires a lot of highly repetitive floating point matrix math. Lighting involves calculating lighting values for each of these vertices. In the early days of PC gaming, the idea was that an onboard geometry processor or hardware transform and lighting could free up the CPU for other tasks required for making a realistic game world, such as physics and AI. We note that the hardware transform and lighting was not entirely novel, since it was available in some specialized hardware. However, the first GPU, GeForce 256, as it was named, was capable of 50 billion floating point operations compared to around 5 billion of professional cards available at that time. And this was what initiated a trend that was quickly adopted by other manufacturers in the graphics card industry. However, the first and second generation from 1999 to 2000, GeForce 256 and GeForce 2, GTS, only offered a fixed graphics pipeline and fixed functional units. So the next development came in 2001 with the introduction of data parallel processors and the opportunity to implement and program individual kernels in the graphics pipeline. Hence, the third series included the same transformer lighting engine as before. However, now it was fully programmable, and it is thus regarded by some as the first true GPU. These programmable units were the vertex and fragment processors, which allowed a programmer to manipulate each vertex and protopixel or fragment that passes through the graphics pipeline. The addition of these programmable units was intended to provide more flexibility with lighting and shading calculations. One key aspect of this architecture was that it followed an approach used in CPUs of providing an instruction set that provided full programmability of the hardware. In particular, NVIDIA introduced a Vertex shader instruction set, which is analogous to the x86 instruction set in a PC processor. The Vertex processor could thus handle the initial geometry set and setup math necessary for the production of the 3D scene that is being rendered. And unlike a fixed transformer lighting engine, it permitted the modification of the attributes of each vertex such that the resultant output can have a different position in space, color, or texture coordinates. The next step in the process is the finalization of the lighting process and the actual rendering of the pixels present in the scene for the final display, which is handled by the fragment or pixel processor. In 3D graphics, the geometry of objects and the environment are made of polygons and given material appearance by textures. Here, the fragment shader makes texturing much more versatile, since instead of just holding values for color, textures can now start to hold variables, direction vectors, and lighting vectors. All of these values can be encoded into the texture. Hence, after the Vertex processor has set up the polygons in the scene and the pixel processor comes in to apply textures, the textures tell the pixel processor what the color of each pixel will be, and they also tell the processor how they will react if certain events occur. So this is all going through the technical details. And this is a illustration of the sort of effects that could be achieved by these pixel and vertex shader units. So using the encoded direction and lighting vectors of a pixel, the pixels can now realistically reflect light through a dot product calculation. And the manner in which the pixel reflects light will change according to the direction of the vector of the light source. So skipping ahead to the next two generations, these introduce greater parallelism by providing multiple vertex shader units and improved overall performance by the introduction of high-performance caches for vertex texture and pixel data. The fifth generation in particular refined programmable pipeline technology by providing a massively parallel vertex shader engine. So while these additional processing units were primarily intended to provide more flexible lighting and shading possibilities, it was clear that they could achieve high computation rates at sufficient precision for general purpose computational problems. Hence, in the sixth generation, around 2004, these units effectively became programmable stream processors that can be reprogrammed for any variety of applications, of which the graphics pipeline is just one. So this gave rise to the stream computing and the stream programming model. In the stream programming model, data is represented as a stream, which is an ordered set of data such as integers or floating point numbers. These streams can be copied, divided, indexed, or used for performing computations via kernels, which operate on entire streams rather than individual elements. Kernel operations may include emulating a function, expansion, reduction, and filtering. A key advantage of kernels is that computation of separate stream elements allows mapping onto data parallel hardware. So applications chain multiple kernels. For example, the graphics pipeline may be just one application now that this architecture is generalized, which may then be implemented by writing the kernels for the Vertex program, triangle assembly, clipping, and so on, and connecting the kernel output of each stage to the input of the next. So this programmability meant that applications unrelated to 3D graphics could be implemented and executed on GPUs. Hence, we may consider a simplified view of the Series 6 architecture in the form of a functional block diagram for non-graphics. In this view, the GPU can be seen as providing a large amount of programmable floating point power and high memory bandwidth, which may be used for compute-intensive applications completely unrelated to computer graphics. So you can see that the vertex becomes data, polygon handling just becomes handling lists, the fragment pixel shader just becomes a data processing unit. So skipping forward to a generation to 2005, the Series 8 chips were a major development since they provided a completely new class of GPU architecture through a unified shader module, which made vertex geometry pixel shader units all run on the same set of extension resources known as stream processors. So this was the G80. So two things, since I need to skip ahead quite a bit. One is that there's decoupling with the shader and texturing units. Second is that the hardware architecture was able to support IEEE 754 single position calculations. And in addition, data could be written out at the end of any unit, unlike previous hardware where data would have to go through the every stage of the pipeline, as though it was going to be displayed. So this was all of great benefit to general purpose computing on graphics processing units. So alongside this was the the introduction of a parallel computing platform known as an application programming interface known as CUDA, compute unified device architecture. How much time? Oh, okay. So anyway, skipping ahead to this. So this is the difference between CPU and the parallelism of GPU architecture. So I included this slide since Mumin was mentioning the book of the master algorithm book. So this is the CEO of NVIDIA who is basically talking about, in these slides, talking about how that's like a major influence for his understanding of how the brain works and how the GPU works. Okay, that's another slide I included last minute. This is showing how GPU performance increases have really vastly exceeded Moore's law's scaling of the traditional CPU architecture. So we're not talking about like incremental improvements. We're talking about like orders of magnitude that GPUs enabled. So like up to 100 in some types of applications. So this clip shows the GPU on one side. So the GPU is, the models being trained and learned, and the CPU hasn't even got started yet. So as I mentioned, so I can skip over this, but GPUs were central to the AlexNet. This is another example of image recognition being done of flowers on a CPU, multiple core CPU, and I'll just skip ahead on this one. So you can see the massive difference when it's being done on a GPU in terms of the recognition of the flowers. And again, this once it's implemented on the servers, I think you can do like a 45. This in 2016, it was at a rate of 45,000 images per second recognition on one server. So basically, you could imagine that full population tracking could be feasible within reach for any government desiring such an objective. So one of the key partners NVIDIA had at that time was HIK Vision, who's been in the news recently for providing such facial recognition services. So I want to sum up on the philosophical implications of all of this. So elsewhere, I argue that Descartes' anthropocentrism led to a theory of knowledge in which man became the absolute foundation for the representation of reality, which is being displaced from a mechanocentric worldview. And his reduction of the physical world, including animate beings, to pure extended matter, based on a mechanistic conception of the natural world, has undergone several transformations via various metaphysical paradigms, most notably via cybernetics and now an informationalist ontology. The consequence of this is that successive metaphysical paradigms, naturalistic, vitalistic, mechanistic, cybernetic, and now computational or informational, have been the basis through which scientists and engineers have attempted to force nature, life, and mind into the conceptual boxes supplied by these paradigms, to use a phrase from Kuhn. The key point is that modern science tends towards the elimination of mind, and hence the portion of reality to which it is assigned, according to Cartesian dualism. In place of mind is a mathematical construction that aims to achieve an isomorphic mapping between inputs and outputs. And in place of mind's home in res cogitans is the creation of a new hyperdimensional spaces in the form of the data structures that not only mediate between the physical and virtual world, but are the microworlds of the microworlds for the artificial minds of artificial agents. In effect, contemporary AI represents a program of reinstalling what is notionally considered mind into res extensa. I mean the philosophical aspect of contemporary AI into res extensa after the collapse of its former home in res cogitans. Accelerating this program of reinstalling mind in res extensa is hardware originally designed for the acceleration of transformations in the Cartesian geometric system of the virtual world of the video game. Hence, the challenge of AI does not only apply to the artificial construction of mind, but also the artificialization of our environment, which is enveloping physical space and becoming a new and controlled shared space of interactions between artificial agents and ourselves. So this is robotic training in simulations, but I wanted to just mention this, which is another aspect of this connection between graphics and artificial intelligence. So this is a game from 1999, which was attracted a lot of interest because of its its ambitious totality engine and revolutionary AI. So they were aiming, the totality engine was basically talking about an infinite polygon engine. Being able to have detail down to the cracks in the street, for example. And also alongside this was a revolutionary AI technique claiming to have 1 million living, breathing citizens within this game world. So who was behind this? So I think some of you can recognize some of the figures here. Demis Haspis and David Silver in the middle over there, who have been more recently saying more grandiose things such as solve intelligence and use that to solve everything else. And David Silver, we've removed the constraints of human knowledge and it is able to create knowledge itself. So with that, thank you very much.